performance machine learning at SURFsara.
Yes. Hello. I'm Valeriu, my full name, and I'm working at SURFsara, the Dutch National Supercomputing Center, and I'm currently working in the recently founded High Performance Machine Learning group. I'm going to talk to you about both our center work and some projects we're actively working on and worked on in the past. So SURFsara is the Dutch national infrastructure and service provider, and it's rather old, the institution. So we started in 1971, and we operate some of the largest infrastructures. You can see a list on the right, but I'm going to focus on the ones that are most relevant for HPC now. And the ones relevant for HPC are our Cartesius system. It's around 2 petaflop system. It's rather old by today's standards and slow, but it still has about 47,000 Intel CPU cores, going from like Ivy to Haswell to Broadwell to KNL, all sorts of Intel CPUs. We also have a partition with GPUs, with NVIDIA GPUs, but it's like a Kepler type K40 partition. Everything is connected by 56 gigabit InfiniBand. Have some lustre parallel file system, but yeah, interesting news is that it's going to be replaced in 2021, most likely early 2021. So yeah, we're going to have a better system, especially for AI, because currently, so the GPUs are rather old for AI, so that's why we made this new infrastructure. It's not new, so Lisa is old infrastructure, but it was CPU focused. Now we repurpose it a bit onto GPUs, consumer grade GPUs. So we have generations going from Pascal to Turing, so Pascal, Volta, and Turing, consumer grade GPUs. What we paid quite good attention on also the interconnect to not be. We realized that latency is okay for many deep learning applications when trained at scale. So then we chose Ethernet over InfiniBand. We also realized that I/O tends to become quite important at large scale. So then we provisioned each node with about 1.6 terabytes of NVMe storage. In the end, we reached quite good FP16 performance, about 17 petaflop. So it's at the moment very usable for machine learning workloads, this system, and it's quite always busy. So that's very nice. And besides systems, we also give expertise support to our users. So we have, let's say, 3 levels of expertise we can offer. On the left-hand side, we have the general research support, where we offer courses, also in the context of praise. We give machine learning courses, GPU courses, and stuff like that. We wrote the best practice guide for deep learning on the praise. And also organizing boot camps, workshops. There is this pretty famous one already together with Argonne and with Tech, called Deep Learning on Supercomputers. It happened already 3 times, and now we're going to have another one in ISC 20. ISC 19, we also had one. We repurposed it to like deep learning for science, more applications that probably are of interest to this community here. So also we offer our users some optimized software stacks for both CPU-based and GPU-based training, and we offer, of course, general HPC consultancy. In the second regime, we would have collaborations with various partners like Intel, Xilinx, and currently even AMD we start. And also with Dutch academia and research institutions like National Cancer Institute or medical centers or yeah, other institutions. I'm going to give some examples of the projects later on. Sometimes our contributions also end up in deep learning libraries, like MKLDNN is the backend of several of the frameworks for CPUs, or MLSL is like some communication layer also introduced by Intel, or TensorFlow, or even in Horovod. Horovod is the distribution layer that works with TensorFlow and so on. So we had several pushes into these lab repositories. And we tend to focus on data pipelines. We see that these hinder performance at large scale quite a bit. Also on the distributed optimization, so really scaling out your neural network training. And also we had some applications, but more limited on inference. And the other extreme, we work on algorithm design, but this less, let's say, because our nature is more as an HPC center, but still we do AI consultancy. We had a project, a program, let's call it like that, where we did that, and we will continue it. So where people try to replace or displace some part of their simulations with some surrogate models or some machine learning models in general. Here, I will go through each of them in a minute. So probably I've just, I will just show you the partners we are working with, and this is together with Intel. So we are an Intel Parallel Computing Center for about 3 years. And through Intel, we went into contact with CERN, for example, where we are training generative models, or with Dell EMC, where we train chest X-ray classification systems or transformer models for NLP. And then also with some medical partners, the Radboud University Medical Center here in the Netherlands, it's where we work on digital histopathology, or the Cancer Institute. Yeah, and also we had a collaboration with a French partner called PlantNet that has a plant recognition system, but I'm gonna go into all. In this, I'm not gonna go into that much detail in this presentation, but I advise you to, if you want, if you're interested to read this white paper, it just went maybe a few days ago on the SURF website. Put a link here. So it's like the technical report of the work we did on these 4 projects. I was telling you before that we had a program. This was the program. It was called Deep Learning Enhanced HPC. And it was run by the SURF Open Innovation Lab, where we had some call for funding, let's say, where we invited people to submit proposals, and then we offered some financial support as well as expertise in machine learning. And they were supposed to come with the use cases. And I think most of them were successful. So the first one on the left-hand side wanted to replace Monte Carlo simulations with variation autoencoder for high-energy physics applications, and they were pretty successful, achieving extreme speed-up factors compared to the traditional simulations, like 10 to the power 6. On the right up side, there is an application from Wageningen, where they want to predict the turbulent flow in the atmosphere. And they did this with a convolutional neural network, 3D convolutional neural network. Again, a 3D application in the lower left. It's like that wanted to distinguish between crystal artifacts and biological interfaces in the molecular complexes, coming from Utrecht University. And then we also had the astrophysics problem, where we explored various machine learning techniques, going from LSTMs to reinforcement learning to generative models for basically simulating planetary dynamics. So exoplanet formation was the goal here. And the results are in that paper, so you can read it for more detail. And we also participate in various European projects. In some, we have more of a support role, like in PRAISE, and perhaps also Combioment for the moment with machine learning, with respect to machine learning, I mean. But we are trying to get a more bigger role. On 2 other projects, one is called ReaxPro, and the other one Examode. We are research partners together with all these institutions you see here. And one is probably also of interest to this community here, of multi-scale modeling of reactive materials. And basically they want to couple all these scales from electronic atomistic scale to reactor scale. Of course, everybody wants to do that. And also Examode is another example where we try to gather information and inform decision makers, in this case doctors, about analysis of both image data, and this is biopsy data, so pathology data, and as well as textual medical reports, synoptic reports. So they want to cross-learn these relationships. This project started about a year ago, and they are running for 4 years. So now the nice research is going on. And we have other activities. We started another call, like the one on deep learning for HPC. This called eTech Big, where we want to empower big science that wants to use AI. And we are part of some other projects around deep learning, but let's go into the use cases maybe. The first use case I'm going to present today is with the CERN Open Lab. We started this about in like 2018, I think. And they all started. So they started the research from the need of computing power. As you can see on there's a chart on the left-hand side where basically they show that they had a problem of Monte Carlo simulations, a lot of Monte Carlo simulations to simulate their calorimeters. And apparently, these Monte Carlo simulations take around 50% of all the world grid from CERN. And they estimate the compute requirements to grow, I think, by a factor of 10 in the next 6 years or 5 years now. So their current methods, the giant force simulator apparently is not suitable, or it is not suitable anymore. So what they proposed was to use a generative adversarial network, a 3D generative adversarial network that just tries to learn. So they transformed the problem into an image-based problem, 3D image-based problem, where they were seeing the trajectories of particles going inside the calorimeter. So that, and basically the generator of this system should be able to generate events following that distribution of events that was trained on. That was the idea. And apparently, from a physics perspective, it worked out within error margins. So that is quite positive. Then we went further, and also the first application only included the energy of the particles. We went further and also included the angle at which particles enter the detector. That also seems to be learned by the model. So and this is ongoing work with the angles. We are always interested in training models at large scale because we are an HPC center. So they had a problem. They were training quite slow at the beginning on a single node. But then with a lot of also single node optimizations, like TensorFlow optimizations, as well as efficient distribution and efficient data pipelines, we managed to get around 90% or more scaling efficiency when going to 128 nodes. That was 2018. But that also LRZ worked on this application. So David Brayford, he scaled the same application on SuperMOOC NG using Charlie Cloud containers. I put the link here to his publication. Also seeing almost linear scaling up to 512 nodes. The most important thing in this application is the inference time, because that's what you want to use the generator for, to infer. And we present here some speed up factors. So basically, this is while generating 10,000 events. So it takes like 17 seconds per event with the actual simulator. And you can see we can achieve speed up factors of almost 20,000 by using some more evolved inferencing with multiple streams mapped to each NUMA node and stuff like that. Second application we are working on now is we call it Deep Galaxy. So we want to deduce the physical properties of galaxy mergers using deep neural networks. So what we do here, we generate a lot of simulation data of galaxy mergers, around 280 gigabytes of image data. And in order to get better precision, we do not want to reduce, we simulate the data at a pretty large resolution. So we have images that are 2048 by 2048. Typically, you would not be able to use GPUs for this, just because of the sheer size of the activations that go throughout the neural network. Anyway, the idea is that the form of the galaxy, the shape of the galaxy, the morphology gives you some idea about the physical properties of that galaxy merger. Yeah, we basically want to train a model on simulated data and then infer it on observation data from the Hubble telescope and get some idea of the properties of the observed data. Apparently, it works out okay. We have an astrophysicist in my team, so he ran this application, and he showed that running a normal simulation would take about 2 days to get the physical properties of the galaxies in a galaxy merger. But this inference only takes like 5 seconds. We're using this efficient net model made by Google. Pretty neat. But an important thing is that, as you can see on the right-hand side, lower right-hand side, you have this extreme memory usage because of the large dimensionality of the input image. So these efficient nets have various flavors of complexity. They go from B0 to B7. On GPU, you can only run the smaller 3 models. So hence, we are using CPUs for deep learning training, and we could get pretty reasonable performance when training on up to 256 nodes. And again, more than 90% scaling efficiency. Another application.
3 minutes, Valeriu.
3 minutes, okay. Then I'm gonna just talk about this a bit. So this is a project started from Stanford University, and then Andrew Ng made a baseline for chest X-ray classification. So there is a data set with 112,000 images. It's a multi-label classification problem, so you can have from 1 to 14 diseases in those images. In the end, we managed to basically scale out this process to 256 nodes. We could train a system that performs a state-of-the-art accuracy and even higher, because we then improved the system in like 9 minutes. That was nice. Maybe I can just talk a bit about this one. Since I heard a lot of things about privacy, we are also interested in privacy, and we run this project with the Dutch Cancer Institute on generating large resolution 3D CT scans. So basically, we want to train a system that can generate really 512 by 512 by 128 volumes end to end. We managed to do so, and why we want to do that is because of privacy again. If we could manage to have some mathematical guarantees that the model does not learn the training data, and we are on that path now, it means that any hospital could just train a system on its own real data and then ship to other hospitals or to other centers artificial data following their real data distribution. So that's pretty nice, and we have pretty good results, again, using CPUs, because you need about 256 nodes, again, each using 150 gigabytes of memory, and you need to use them for about 8 days to get this model. So yeah, and I can just in the last seconds, I can maybe show you how it's learning. So it's a progressive growing of GANs type of model, where the feature maps are growing as the network learns. So you can see at the beginning very small features, and then they grow, the images that are learned, and so on. And then you could already see some of the details. These are fake, basically fake patients. And yeah, it goes all the way up to this large resolution. Then I'm not going to go into this. Then yeah, maybe just to show what we are, let's think what we are focused on. So on this chart, we could see many people are working on benchmark type of problems, where their input data is small and their model is small, or in this regime, where they can run on GPUs technically. We also did some applications in this regime. CERN is a bit out because of a bit larger input data. But then the others, as you can see, the AI radiologist that we did with Dell is already here. It's pretty big. You cannot run it on GPUs. What we do with the Netherlands Cancer Institute is here, and what I didn't have time to talk about, the Radboud UMC, we have images that are of this dimensionality, so it stays about here. So next things for us are to focus on different types of parallelization, such as model parallelism and pipeline parallelism, because we cannot even do it with CPUs at this stage. So yeah, that is my team, and yes, that was my talk. Thank you.
Thank you, Valeriu. I feel a bit guilty that I chased you to hurry up when in fact we have so much extra time. If you have any if you have any slide that you feel that you wanted to spend more time on, particularly regarding machine learning at SURFsara, then I think we have time to have one more slide. If you have something pressing.
I can maybe just spend a bit more time on this one, because I particularly like this application. I can give a bit more detail on this one.
Please do.
That I just, yeah, with the progressive growing of GANs. So why we want to do this? So it was about privacy. So this would empower hospitals to just be able to share their data if they would have mathematical guarantees that the data is not being learned by the model. And there are ways to do that. So there is this differential privacy type of training where you can make sure of that. But then looking ahead, so we have the capability to generate these extremely large volumes. Looking ahead, we want to be able to use this in practice besides sharing data. And another application is radiotherapy treatment plans. So what happens usually is that when a person goes for a radiotherapy, he gets a CT scan at the beginning of the treatment plan. And then every day they are not allowed to take CT scans again until the end of the plan, because they are just too high dose. So what they do, they have this cone beam CT scan or low dose CT scan that they can take every day, but then for that one, the resolution is not only the resolution, the contrast as well is not sufficient. So the doctors cannot take really good decisions. They just use it a bit for information, but not of very tremendous help. So what we want to do here is to use this architecture that we created and condition our generation on the cone beam CT scan. So basically, if you would know the mapping between a cone beam CT scan and an actual CT scan in 3D, you could generate CT-like quality from cone beams that can be taken daily. And this has pretty big potential of improving clinical treatment in radiotherapy planning. So I think that's what I wanted to say.
I'm interested in the idea of patients revoking their permission to use their data once the data has been anonymized. I think this was briefly mentioned here, but certainly mentioned in the first talk.
Mm-hmm.
If the data is truly anonymized, then surely how do we know what data to delete if a data decides to withdraw? And of course, under GDPR, you're allowed to retain data under operational practices. So perhaps truly anonymized data, we can retain that even if well, yeah, I don't know, I'm at the limit of my understanding.
Yeah, it is. I think it's, yeah, these regulations are pretty complex because, okay, let's say we managed to give mathematical guarantees that the model did not learn the training data, and the person says, I don't want to use my training data or my data, then you have used the data to train the model, although the model did not remember it. So I don't know.
Yes,
I don't know exactly how that would go, but yeah.
Yeah, it's entwined into it's embedded into the logic of the neural networks.
Yes, but it will help. It would help tremendously with the bias that these models tend to have. Because of course, if you train a model like this on the Dutch population, you cannot expect it to work on populations from all over the globe. So, and it is unlikely at this stage in time, at this point in time, that we will get equal amounts of data from health systems all over the globe, such that we can create a global system. So yes. That was this is our aim to go into this direction of differential privacy to generate fake data.
Okay, is there any other questions for Valeriu?
Can I just check the James from UCL? I must admit it was my understanding under GDPR that if your justification for using the data was a public task rather than consent, then you weren't under the same obligations to remove sensitive data on request. I'm not a lawyer, so I don't know if anyone else can back that up or conclusively dismiss it, but that's the impression I was under.
James, sorry, you turned a bit robot there. Could you have one more go at saying that?
Sorry, what's that?
Your audio was very intermittent, and it sounded like a bit of a robot. Could you say that?
I'll try again right next to the speaker. Is that any better?
Much better.
Much better.
Much better. Okay, yeah, I was saying that I am not a lawyer, but it was my impression that if you use public task under GDPR as your justification as data controller, you are not under the same obligation to remove data at the withdrawal of consent. I don't know if anyone else can back that up or tell me I'm completely wrong and it's only a matter of time before I'm fined a huge amount, but that was the impression I'd been given by colleagues.
I am not sure, so I also am pretty. We are quite concerned about this GDPR, but we, of course, we don't know. We are not lawyers as well, so I don't know.
Yeah, okay.